Good afternoon, everyone. I am your host, Shailesh Shukla. We will be starting the webinar very shortly. Thank you for your patience. Good afternoon, everyone. And really thank you for your patience. I hope you're doing well. On behalf of Advent Informatics, I, Shailesh Shukla, warmly welcomes you to today's webinar on a highly practical and insightful topic, which is From Molecule to Insights, Mastering Instant JChem and Plexus Connect. We're delighted to have you with us, looking forward to an engaging session filled with knowledge sharing and real-world applications. Before we move into this sessions, let me take a moment to introduce the organization behind this event, which is Advent Informatics Private Limited. Advent is situated in Pune. It is a leading distributor of advanced life science software solutions. Our expertise spans chemoinformatics, molecular modeling, medicinal chemistry, chemical data curation, and biological information management. We proudly serves a wide range of clients from leading pharmaceutical and chemical companies to CROs, academic institutions, and government R&D labs across India. Our mission is simple yet impactful to bridge the gap between scientific challenges and software solutions by making world-class technology accessible to Indian researchers and professionals. So Advent Informatics is honored to represent globally renowned technologies partner, including MoleSoft, Chemexon, Campus, and Satara, Transgene IT Solution, and Key Module. With their support, we continue to empower discovery, innovation, and collaboration in the life science domain. It's now my absolute pleasure to introduce our today's speaker, Mr. Surojit Sadhu, CEO and founder of Advent Informatics Private Limited. Mr. Sadhu founded Advent Informatics in 2016 with a vision to bring global life science technologies closer to Indian researchers. He is a bioinformatics graduate with extensive expertise in handling chemoinformatics tools with over 14 years of experience in the field. Mr. Sadhu had played a pivotal role in introducing and establishing global brands such as, you can say, Chemexon, MoleSoft, Key Modules, and others in India. His unique combination of technical expertise and leadership makes him the ideal guide for today's session on From Molecule to Insight, Mastering Instant JChem and Plexus Connect. So please join me in welcoming Mr. Surojit Sadhu. Sir, the floor is yours.
Thank you, Shailesh. I guess I'm audible, right?
Sir, you are audible.
And my screen is also visible.
Yes, sir.
Okay, great. Hi, everyone. I'm Surojit, and I'm going to present and demonstrate today how we convert molecules to insight, or rather, in a more crude way, how we can convert data into insights using Instant JChem and Plexus Connect. Now, Shailesh has already mentioned it to you guys. I will skip this. So one of the things that I would want to highlight about this is that we are very highly appreciated for our support by our clients. We try to be as responsive as possible, and on a survey that we conducted in November last year, we were also pleasantly surprised to see how our clients love our responsiveness. These are some of the companies that we are representing. Today, we are going to focus majorly on Chemexon. Apart from Chemexon, we are also representing MoleSoft, which is into molecular modeling, all kinds of docking, virtual screening, and stuff like that. Then SCM, which is more into computational chemistry, material sciences, quantum, and all this kind of thing. Then Transgene is for ELNs and things like that. Then we have Campus, which is an AI-assisted lead discovery platform. So there's different modules to grow your molecule within the active site, then to predict the reaction synthesis scheme, taking care of the cost of the scheme also. Then Key Module is for conversion of images of chemical structures into editable chemical structures. And Satara is majorly for an integrated data analysis and data visualization tool. So we are representing the D360 portfolio. Some of our clients, quite a few are there. It's a subset. Some of them are all still missing. We have not added them. But then coming to today's topic, why is this important now? Right? We are in the age of AI, ML. We all talk about AI and ML, right? But then what we are missing a lot of times is data that can be converted into insights. So how are we storing our data? How are we managing our data? Is it actually usable in any of the AI as an input, in any of the machine learning as an input, right? So if you have been following this domain carefully, you can understand that every 2 years, the data is almost doubling, right? So when we talk about data in chemistry particularly, so what are the kinds of data we are talking about? We are talking about structural data. Let's say chemical structures, it can be small molecules, it can be reactions, it can be generic structures, it can be Markov structures from patents. They're increasing day by day. Then associated with them, we also have the experimental data, which is screening results, the synthesis outcomes, field reactions, all of those data. Then we have associated data, that is analytical data, spectroscopic data, chromatographic information, all different kinds of like instrument data that we generate for the chemicals. Then, of course, last but not the least, one of the most important one is the biological data, right? So if you are working on NCEs or any kind of drug molecules, then what is their activity, toxicity, pharmacokinetic properties, and things like that, right? Now, the challenge here is that traditional methods cannot handle the complexity of this data, right? It looks very simple, straightforward, but then it is not as simple as it may seem to be. So traditional methods of storing data in Excel sheets, in traditional databases are not good enough to handle this complex data. Now, what are the problems in data management, right? Particularly in terms of the chemical data management. That data is very heterogeneous, right? So if you remember, we talked about small molecules, like which are individual complete structures. We also talked about chemical reactions. These two by themselves are so very different in their data structure, right? So they're very, very heterogeneous. And then there are different standards, there are different ways of storing data, there are different formats of storing data. You might store it in as an SDF file, you might store it as an MRV file, in an RDF file, RXN file, so on and so forth, right? Now, as the days has been progressing, you know now, like all the chemical vendors are offering screening of maybe around a trillion molecule libraries that can be screened, right? So the scaling is also an issue for traditional databases. Now, there are also very complex relationships in chemical data, the structure activity relationship, the property correlations. Then the other challenge is that the data is still in silos, right? So people are generally still sharing SDF files, Excel files. There is no system. People are generally, I should not say no system, there are systems, but the people are still generally not using systems that enable them to have live sharing of the data. Now, again, the quality concern are there because the data is inconsistent, the data is not standardized. So that concern also has to be taken care of, right? Like as I mentioned earlier, also spreadsheets and basic databases are insufficient for chemical intelligence, right? Because they don't have any inbuilt chemical intelligence. Now, why do we need chemical intelligence? Why does it matter to have chemical intelligence in databases in which we are storing chemical data? For sure, people who are working with it, you would know that we should be able to do structure-based searching, right? Substructure, similarity search, duplicate search, full fragment, all of this kind of search. We should be able to do chemical standardization, right? Standardization is nothing but the normalization of molecular representations. That is because, as I said, the data is very heterogeneous, not just in the type of data, but you can draw the same chemical structure in multiple different representations, but maybe all of them might be correct because it can be represented that way. So it is very important to standardize the data. Then also what is very important is to handle the stereochemistry. There can be molecules which have tetrahedral stereochemistry, cis trans representation, different isomeric forms. It is also it is also important to handle those stereochemistry representations. So a typical system which can handle chemical data should be able to handle these kind of properties also. Then obviously property calculation based on the chemical structures, relationship modeling, they should be able to understand or identify the trends. If you want to do an SAR analysis, you should be able to do a SAR is nothing but a structure activity relation. You should be able to do that. You should be able to see the molecules in 2D, 3D as per your requirement and as and when it is needed. Right. So chemical data, as you have by now understood, that requires specialized informatics tools also. So it is not that the traditional tools will be able to handle this kind of representation and this kind of data. Now, why again the need for specialized tools? Just a small quick recap of whatever we have done, seen in the last slides. Basically, traditional databases have limitations because they cannot handle chemical structures natively. Right? If you are handling chemical structures in a traditional database, you will be storing the structures as smiles or as IUPAC names and searching through smiles, which are not optimal. Right? Then they lack substructure and similarity searching. There is no inbuilt chemical calculations. You have limited visualization capabilities and poor integration with chemical workflows because they are not meant to be integrated with chemical workflows. Now, why Instant JChem was developed, right? So we will go into the details of Instant JChem in the next slide. So, but then the core idea was that Instant JChem was developed to bridge the gap between chemistry and informatics, right? So the idea was that you should be able to handle your chemical data. Being a chemist or a biologist, you should be able to handle chemical data efficiently without the need to do any kind of coding or handle any kind of databases and like in kind of data without being a database administrator as such. Then it was developed to provide chemical intelligence out of the box, as you will see in the demo. It is very scalable. It's a very scalable database management, and then it supports collaborative research workflows. So that means that you can share the data with your colleagues. They can edit the data in real time based on their access rights. They can share their data in real time, and you have the data ready whenever you want to see it. Now, a basic introduction to Instant JChem. So Instant JChem basically is a very comprehensive desktop application for managing chemical and associated data. The associated data can be biological data, toxicological data, any kind of data that is related to the compound. Now, the core philosophy is that it is very database centric. So it's built around the RDBMS, that's a relational database technology. It supports multiple different databases. If you have a PostgreSQL cartridge at the back, PostgreSQL database at the back end, it supports that. MySQL is also supported. Oracle is also supported. Microsoft SQL Server is supported. So most of the major database technologies are supported. Now, it is chemically aware. It by default understands chemical structures. It integrates Marvin Sketch as well as the JChem engine. The JChem engine is an industry standard for handling chemical structures. So Instant JChem integrates JChem engine at the backend to handle the chemical data, and for viewing and like editing purposes, we have Marvin Sketch embedded. It is scalable. You can handle as low as 10 to 20 structures, or you can handle as large as like let's say 100,000 to 200,000 or even more than that. So when we handle multi-million data, then we have other solutions to handle that data, not Instant JChem, because the GUI obviously will lag if you're having multi-million data. Now, it is also very user-friendly. There is no programming required for basic operation, or more, even the most advanced operation does not require any kind of programming until and unless you want to change the default behavior of Instant JChem. It is extensible, as I just said. It can, if you want to change the default behavior or you want to extend the functionalities of Instant JChem, you can customize it to do that. Or if you want to automate certain workflows, you can also do that in Instant JChem by customizing it using Groovy scripting. Now, some of the other key features of Instant JChem are that the key major things that you would want to expect, or that you would rather expect from a database, would be it should be able to manage your data properly. It should be able to retrieve your data properly, right? Storage without the functionality of getting data or getting data retrieved is of no use, right? Because it then becomes a black box. You then again have to scroll through the data to view the data. Now, in terms of the data management, there are multiple import and export formats. Like you can import from SDF, Excel, CSV file format, MOL file format, and things like that. So there's a wide variety of file formats that are supported for import as well as for export also. Then by default, there are some standardization that are automatically applied so that the structures are normalized. You can also specify other standardization from the interface that will be applied to your database based on your own business logics. It by default supports built-in molecular descriptors, property calculations like of the log B, log D, all of these things can be done. It can detect duplicates. So, for example, if you have collected data sets from multiple sources and you want to ensure that your chemical structures saved in the database are unique. So, when you are importing the data, you can check for the filter that says that duplicate filters. So, filter duplicates rather. So, it will automatically filter out all the duplicate chemical structures based on the structure of the molecule, and it will not import any duplicate structure. So you will have a unique set of compounds in your database. In terms of search and query, we are going to discuss more about this also, but then we can support substructure search, similarity search. We can have combined queries, that is chemical as well as non-chemical criteria can be searched together. You can have saved searches, like there is something called as lists in Instant JChem that you can see in this screenshot here. Over here, you can see that there are these temporary queries, temporary lists. So these are basically the queries that you have done. You can save them so you don't have to run the same queries or write the same queries again and again. Now in the search and explore, again, there are multiple different ways of doing the query. There is a form-based query that we will be using today during our demo. And there is a query builder also where you can, this is the query builder, where you can use multiple different conditions. You can have and or operators so that you get your desired result. So in instance, you can, like I always say, you can make the query as generic as possible or as specific as possible to address your problem statement. You also have chemical terms filters. So typically, let's say in terms of the chemical terms, for example, let's say you want to find out that if I have a structure query, is my molecule also following the Lipinski rule of 5 or not? So in instant JChem, it is not mandatory for you to have the Lipinski rule of 5 calculated previously to do this filtering, right? So when you're doing a structure query, if you do that chemical terms filter over here, if you see here, there is a chemical terms filter over here. So if you can just click on this button and you can get the chemical terms, it will at the back end calculate the filter, find out if a molecule passes the filter or not, and based on your condition, it will give you the result. So again, in terms of the structure searches, there are multiple different kinds of structures such as substructure, superstructure, full fragment, similarity, duplicate. As I already mentioned, you can have complex and or logics. You can search domains, like if we have something called as the federated search, where you can search multiple databases at the same time. Now, these are the other options that are there. Like once you have done the query or you have got a result, you can apply all these operations so that you don't have to run multiple queries again and again. You can combine your queries and combine your lists. To view data, you have something, there are two kinds of views rather. One is a grid view and the other one is a form view, which will be discussed in the next slide. So the form view basically, this grid view basically is the, let's say a spreadsheet kind of view. Okay, it looks like a spreadsheet. Obviously, it is not like an Excel spreadsheet, but it is much more than that. But it's a spreadsheet like a view, right? You can do conditional formatting. You can change the formatting of the, how the appearance of the columns are there. You can reorder the columns to suit your visualization needs. This is the form view. The form view is more, it is much more customizable. You can create your own forms. Then it is also very useful when you want to see multi-dimensional data at one go. So let's say, for example, in this case only, you see that the structure is there. There is one structure that is associated with multiple KI values, right? So you can see that entire data in one single go. So if you have data coming from multiple different sources, which has multi-dimensional data, like 1:many relationship, form view is one of the best ways to view the data. The form view also allows you to create analysis options, right? Like in terms of analysis option, I mean that it helps you to create scatter plots, radar charts, spider plots, and all of these kind of histograms and things like that. Now, moving from the core IGC capabilities, there are some advanced capabilities also, like conditional formatting. You can generate charts. You can do data pivoting. There are some correlation analysis. Clustering can be done. Then in terms of customization, as I already mentioned, you have form design. Groovy scripting is required when you want to automate or you want to extend the features of the IGC. There is a public API that can integrate with external tool. Like for example, we have now connected this with Chemwell. You can directly fetch data from Chemwell into instant JChem. And it's a plugin architecture, like extended functionality. Like for example, I said, if you want to calculate properties, you can do that. That is by default embedded as an plugin. The calculator plugins are embedded. If you want to do reaction-based enumeration, you can do that also. The reactor plugin is also embedded within instant JChem. So this is the analysis part that we already discussed about. So as you can see here, we are looking at the scatter plot. There are 4 different scatter plots, but in each scatter plot, if you see, we have the molecular weight on one side, and there's the field number 2 on the other side. Then the coloring is based on one of the third field, and the size of the dots are based on the 4th field. So by looking at these 4 scatter plots itself, you can see that we are having 16 different fields in our view that we can analyze. All of these charts and graphs are synchronized with each other, so that if you select any of these, it will directly select it the same in all of these and also in your parent data table. So this is a molecule matrix. We will also see this when we are doing the data. So if you see here, It has the structure of the selected. You can see this is the selected structure. This is one of the 3 structures that are selected here. It also has an additional field like the mole weight, and it is also conditionally formatted. So there is very quick look at it can give you an idea about, okay, where is the molecular weight or where is this additional field ranging from. Now, I talked about standardizer. So basically, to standardize the structures in Instant JChem, we have integrated standardizer, which is also available as a standalone product. Right, the standardizer basically transforms structures from different representations to a standard canonical representation to eliminate database inconsistencies. The thing is that to the human eye, different kinds of representation might still be understandable, but the computer, we have to explain it to it that, okay, these two are the same structures. For example, if you're talking about an aromatic structure and a non-aromatic structure, if you are aware of smiles, you know that the smiles are also represented differently, right? So of course you can understand that the computer treats them differently. So the standardizer tells the computer that, okay, these two are the same structures. So let's say, for example, if I'm talking about an aromatic structure, when I'm standardizing it, I will either aromatize all the structures that are coming into the database or de-aromatize all the structures that are coming into the database, so that there is one single consistent representation, right? And this is very important if you want to get structure-based, structure-based search results. This is also very, very important when you are dealing with or when you are inserting these kind of chemical structures into as a training set for your machine learning or AI-based algorithms. Now, for example, this is what I was talking about. These are the different representations of the same structure, right? Some are aromatic, some are alternating single bond, double bond, some in which hydrogens are mentioned and which hydrogens are missing. So standardizer basically converts all of them into one single structure. Now, it does not delete the original structure. It also keeps the original structure format in the database, but it tells the database that this is the representation that we are going to use internally, right? So if I search for this, I should get all of these results. Now, there are lots of standardizers, around 60 such standardizers there. You can edit them, you can add your own, you can do all of these that we are talking about. Like, for example, I talked about aromatize. You can do cleaning in 2D, 3D. If there are salt forms, you can keep the largest group. You can see that you can remove fragments, you can remove explicit hydrogens. There are lots of things that you can do with the standardizer. Now, also integrated with the Instant JChem is the calculator properties, calculator plugins. So basically, these are calculations and predictions that are there in Instant JChem. So what this do is basically you are able to calculate different physicochemical properties. By calculate, I mean predict. Now, Chemizon is a world leader in terms of physicochemical property prediction. So one of the best ones are the PK, log P, log D. So this was a PK prediction for from our end. So you can see that the 50% of the data that we talk about here has a delta of less than 0.5, which is a remarkable achievement. Then there was also this sample challenge in which we did not participate, but then once the data set was released, we actually compared our prediction with the ones that we were also able to beat all the other methods like physical-based, QM-based, MM-based methods. There are lots of publications that are available and lots of internal case studies that has been done to understand how accurate these predictions are. So basically, the accuracy of these predictions are basically validated by understanding how close are they to the experimental values. Now, Plexus Connect. Plexus Connect is an extension of Instant JChem. So what do I mean by extension? It's a web-based tool, right? So it's a thin client tool, that meaning that you don't need to install anything at your system. You just need to visit an URL, log in with the username and password, and you will be able to see the data that has been shared with you. And you'll not just be able to see the data, you'll be able to filter the data, analyze the data, browse through the data, download the data if you have download permissions and things like that. So what are the key features? It's a web-based, no client installation is required. It is integrated with IJC. So meaning that if you make changes in IJC, they will also be reflected in your Plexus Connect projects. You have the chemical and search-based queries like you have in Instant JChem. Multiple users can use it. If you are storing the data in a central server, then multiple users can log in and use the data at the same time. it has very responsive design. You can also access this in your mobile phone, in your tabs. It is touch enabled. You can draw the structure using the Marvin JS that is integrated, and it is touch enabled. It also supports Python for data processing. You can export it, as I said, and obviously the security and authentication is in place so that you can view it from anywhere you are without worrying about the security of the data. Now, in terms of the visualization, which we are also going to see today in the demo, we have very good interactive charts, and then we have very good graphics for structure rendering. There are custom analytical views. It's optimized for mobile and smartphones, as I said you. But then let us go into the demo and try to see the data in real time. Okay. So before I start with the demo, so let me show you the data that I have handled using IJC and Plexus Connect, right? So this is a sample data that I have downloaded from Campbell, but then typically you can understand that you will get data from different sources. It will be something on these lines, like if it's a CSV format or an Excel format, it will be in this kind of format. Okay. So there are around 8,000 or 9,000 rows in this. I'll just wait for Excel to open it up, or in the meantime.
Meanwhile, if you have any questions related to topic, so please feel to type them in the chat box.
Okay, so this is the data. This is a CSV file. So there's lots of information, lots of things in there, but then it is very, very difficult to understand from this, right? The best that we can do from here is that probably we can open it up in an Excel and then get the data formatted in an Excel sheet where we have the smiles and everything over here. Let me just go back to this. Sorry. Okay, so let it be. I guess you understand that how complex the data is. Now, what I have done in Instant JChem is, let's say, for example, if I have that data, okay, let me try to open this off for you first. Okay, just give it a moment. Sure. Okay, typical demo effect. Let me just quickly kill Excel and just get it restarted again, because I believe the data is quite large for it to handle. So as I said, I downloaded some data from Campbell. Now I'll try to open that up. So this has around 850 odd structures. I hope it opens up in Excel this time. This was around 800 odd structures, and you will see that the data is very, very huge. In case it does not. Okay. And there are data points that are ranging from by activity data to target information to assay information. Looks like Excel is not in the mood to cooperate today. So if you can see, this is particularly one particular value, right? If I just scroll down, so there are around 8,000 odd entries in this particular sheet, right? that is in the CSV format. Now you can see there are around more than 8,200 odd entries in this file. Now, can you imagine how many unique structures are there in this? There are 8,626 entries in this file. There are approximately around 850 odd molecules only that are unique in this, right? So what I have done here is that I have cleaned the data a bit. So this is now the structures file. Now you can see all of these are the smiles. They have the Campbell ID and the smiles here only. Now there are around, sorry, this is the complete set. So 7,200 odd structures. Now what I will do is I will go ahead and I will create. Let me connect this. So now I will create a new data tree. Okay. So we will leave this as it is. Now let's say, okay. Now, as I was saying, we have a duplicate filtering option over here. So I will say duplicate filter duplicates, right? Or other duplicate filtering here. Now it has created this field or this data table. Now what I'll do is I will import it here. And what I'm going to import is the file that I have showed you. Let's show all the files, and we are talking about structures. Right now, I will just go ahead and say the first line is the field names, and I have the molecule Campbell ID and the smiles. Right now, I would want the smiles to be mapped to the structures, so I have removed the smiles from this, and now what I'm doing here is this two needs to be mapped. So now it will convert the smiles into structures and put them in the structures column. Okay, so there were 7,500 something structures, right? Now I have started to import it. Now you will see that it will automatically apply for the filtering. It will just take a minute to get the import done. Now you can say it has already started importing, and it is giving warnings, right? So these are not imported because a duplicate of CD I did this in this particular database, right? So you can see it will always keep every time. Okay, whenever we are switching on the duplicate filtering, the import will be a bit slower because it is checking each and every structure because it is before it is being imported, right? So I'll cancel this. So this is what you get after you have imported all your structures, right? So there are around 800 odd structures. 22 unique structures are there. So this is what happened. Now I can do you see how beautiful this looks, how easy is it to understand and analyze the data here, right? So what we have done here is, let's say for example, in this case, we might have imported some structures here, which we stopped. So what we have done here is we have around 278 structures here. What we have done to go from here to here, that is this grid view, is that we have calculated. You can see there are a lot of physicochemical calculations that we have done, right? The predictions. So what we have done here is we have the grid view. Now, if you go to chemical terms, you can see there are lots of these chemical terms that are there, right? And if I press Control and space, it will give you even more options over here. So for example, we will calculate the CNS MPO, right? It will validate the expression, and it will, if I say finish, it will start calculating it, right? Then I can also calculate some other things like, let's say that maybe the log P here, right? So now you can see that we have the log P here. We can calculate the log P. Then if you have a pH dependent value, right? Let's say the pK or anything like that. Then you can specify the pH. Then if you have the log D, if you have log D, if you want to specify the pH in a different way, this is basically an editor. As you can see, you can do that. So I can calculate that also. So similarly, we have pre-calculated a lot of these values in this table. And then what we have done is we have used the conditional formatting inbuilt within Instant JChem to give this heat map kind of a look, right? So if I go to the grid view and say I select the CNS MPO, if I right click, I can sort it by ascending or descending just to understand the range. For example, it starts from 1.5, and if I sort it descending, it's still 6, right? So if I select this particular column, or even if I right click and say conditional formatting, and I can select any of these templates that I have. Let's say, for example, the traffic lights template, right? So this is the by default green, yellow, red. If I want that there should be more than 3 categories over here, I can add another category. Let's say a new category, and I can say the background color would be, let's say, this, right? So now what I can say is that anything that is, let's say, between 1 to 3 will be of this particular new color. Then anything between 3 and 5 would be yellow. Let's say between 5 and 6 is green, and anything that is greater than or equal to 6 is red. Okay. Now I'll just say that unsort, and if I want to see the data nicely, I can just resize this. So you can see that I have got this data. Now, if I switch back to the pre-calculated data, I can see that very easily if I just go ahead and resize the cells by just dragging from here, right? I can get a very, very clear understanding of how my data is distributed, what are the trends in particular sets of data that I have. This I have used the blue scaling. These are all the same things that that we are talking about, right? So for example, I will just unsort this also in this case. Right. So you can very easily understand how the data is very distributed over here. Now, this is when we are talking about visualizing the data in terms of the grid view. Now, there is another view that is called as the form view, right? That we discussed. Now, you can understand that this is just one data table, right? I have imported all the other data table, like the assay data, the bioactivity, right? Let's say if you see the assay data, it does not have any structures, but it has the molecule ID along with all the other data values. Then we have the bioactivity data. Same here. We have grid view and with the ID and all the other values. So what I've done is I've created a relational database, and I am able to see all of the data in one single view over here, right? So as you can see, it is very easily visible. I can just go ahead and scroll through them, and you will see that this is a one-to-many relationship, meaning that one single structure has 3 different IC50 variables calculated. There are different, like chemical IDs, assay IDs. There are different target data that is there, and there are different physicochemical properties that are calculated. Now, it is very easy to view the data over here. Now, what I would want to do is I would want to do a structure search. So as I said during the presentation, we will use the form-based query. We'll go to query. We will double click here, and then we will just draw the structure. Right. Let's say I would want to draw now I have the option to select which kind of structures I want to do, like a substructure or superstructures or something like that. So we have 822 molecules. I will just draw the single molecule, single scaffold, let's say, or the part of the structure, and I would do a substructure. So then I'll run the query. Okay. So now initially the first query takes the largest amount of time when it is loaded to the memory. So it will do the search and we will see that it is running the query and we will get there. So you can see there are 51 molecules that we have got here out of the 822 molecules. Now it has satisfied my structure based query. Now what I want to do is I would want to add some other data also, like in terms of the querying option that I have, right? So let's say, for example, in this case, what I would also want is I would want the assay organism is equal to, let's say, Homo sapiens, right? And I run the query. I get 48 hits now, right? There are 48 hits out of 50 which are in Homo sapiens. Now let's say I would want all the data from the database where I have an IC50 value. Okay, irrespective of whatever value it is, there should be an IC50 value associated. Now I'm running all of these three together. There are just 12 hits which has this substructure. The assay organism is an Homo sapiens and has an IC50 value, right? So I can go on and do the filtering as I want, right? Let's say, for example, if I draw a much more generic structure, and let's say I remove these, then you'll see that I get many more number of hits, right? Then what I can do is, in that case, let's say I would want to say the CNS MPO is between 2 and 4, right? And I run the query. So any fields that you see over here can be used for our searching, right? It is very straightforward. Now, what else we can do is, we talked about analysis, right? So in the analysis part, you see that we have graphs and charts, right? So we will go to query. I will clear the query show all. So this are the charts. Let's say, for example, in the form view, there is a design window also. We will not have time to show you the design window now. But let's say, for example, this is the design where you can design your own form. Let's say I would want a scatter plot. In this scatter plot, what I can do is I can have the, let's say, can have the, like I have created the CNS MPO, then I can create this log P. Then in data points, do I want to, based on what do I want to calculate? I would want to point size based on log D, and the category field is by, let's say, rule of 5. Okay. So once we do that and we go to browse, you see that we can create this kind of data. Now, what I can do more in that is that, let's say, I will put a molecule matrix over here. Okay, I will associate it with the structure, right? And over here, I will go to the customize widget settings. I will show you 3 by 3. And I would want an extra field. Let's say I would want the log P to be added. And if I want, I can also use the conditional formatting over here. Okay, I'll not do that right now. I'll just say close. I will go to browse. Okay, now let's say I select these particular 4 structures. Now they will be selected anywhere in this, but then what I can do is I can just go here and I say, show me the selections only, right? So then it will just show those particular point selections. There are 7 structures that are there that can be shared here, seen here, right? Now, quickly, I will quickly log off from here and I will show you that you can do the same things in Plexus Connect. Okay, so let me quickly start Plexus. Okay, you don't have to do this every time. Now, since I'm using it in the same machine, I generally have to do this. Now, once it is started, all I have to do is, let me close this, and I guess everywhere it is the same. I don't know why, but then the system seems to be running slow, which is not normal. Okay. We'll just require another couple of minutes to get this started. So this is by default. If you're using it as in a client server architecture, it will automatically be started all the time. Now, once that is started, we will say it is deployed in my local host. So I'll say localhost 8080. Okay, it is still initializing. Yes, now it has started. So let's say I am a registered user here. My administrator has allowed me. I can just say login. And now whatever data you saw in Instant JChem, like for example, the grid view, I can see the same data in Plexus also, right? Remember, you had the conditional formatting and everything that we had there. So I can see the same data here also, right? I can go here and double click, and I can fire up Marvin.js, and I can edit the structures if I am allowed to do so. Similarly, what I can do is I can go to filters. I can also, let's say I say this, that, sorry, I will add this structure as a filter here, and I can do the same query that I did there, right? So for example, I can do a substructure query. It will query the database and it will give me the results. You see, there are 822 structures here, and it will then filter, and I can similarly, you will get the same 51 results over here. You can similarly, you can see that here also you see the hit highlighting option is there. So it will highlight the part that is matching your substructure query. Similarly, I can go on and add as many fields as I want that I was doing there in that case. Now, what I can also do here is that I can also go to a single molecule view that you saw earlier. And again, it is the same form that is there. I can again use this form, and you can just query it directly from here. What is also interesting is if I go to the grid view of molecules, single molecules, so I can use all of this data to plot charts here, right? So obviously I have done that in Instant JChem, but what I can do here is I can go to scatter plot over here. And in this case, what I will do is I will just say that let's say, for example, on the horizontal axis, we will have the CNS MPO, vertical axis, we will have the log P maybe. And then we will color it by based on the Lipinski rule of 5, and we will have the size based on the number of you can choose anything. Let's choose the rotatable bonds, right? Now, if you want additional fields, you can have based on different shapes and things like that. So let's say accept or something. If I want additional, I can do that, right? I just say add. It will plot a chart. Now you can see. So obviously it is not in that category. So this gives you a density map, and as well as I zoom in, I will get to see the individual structures. If I put my cursor, it will show me that. Again, if I zoom out and I just select, there are multiple ways to select. Okay, this is a rectangular selection. If I go here, there is a free form selection, free form deselection. So the free form selection, if you select, and you can go ahead, and select this, and I can just select any of them, right? And then if I just go ahead and say deselection, it will deselect that I have selected, right? Now, what else can be done over here is that you have this, you can add regression models over here. So if you want to, you can add these also. Now, other charts also can be imported. For example, we can put a radar chart, right? So in terms of the radar chart, let's say I will quickly do this for log D. Then we will have hydrogen bond acceptors maybe, and then molecular weight and okay, so I'm just showing you to show you the functionality. Typically, when you are having to generate a radar chart, you should be normalizing the values and then adding that for the same thing, right? So then it will create a radar chart where you can analyze the data. Okay. Probably I added something that was not needed, but this is what I wanted to show you, that you can add all this kind of data and you can analyze the data very, very easily. Let us see that you can do R group decomposition also. You can sketch the scaffold here, and you can, so for example, I'm not going to run it. I don't have that much time, but then, so for example, let's say there is a R group here, there is a R group here. I select this and this, then I click on OK. It will run the R group, they do an R group decomposition. It will have the functional groups on X and Y and your properties that you have selected along the matrix. So I guess that is all from my end. If there are any questions, I am more than happy to answer them. Shailesh, over to you.
Yes. So we received few thoughtful questions from our audience. So the first one is, can I import structures from PDF to Instant JChem or Plexus Connect?
It depends. If actually the straightforward answer would be no, but there is a additional tool called as document to structure in Chemexon, which can read text. If your chemical structures are in SMILES or in text-based formats, then you can use that document to structure to import. Alternatively, if your PDF contains good quality images of chemical structures, you can use key modules Clyde to convert them into SDF, and then that can be imported in Instant JChem.
Okay. So can I export structure from the 3000 format to Instant JChem?
You can export from Instant JChem to in V3000 format, yes.
All right. And the last one is it possible to integrate Instant JChem with other research tools?
Not really. See, the idea of Instant JChem is, so JChem engine can be integrated. So JChem is the core that is running behind Instant JChem, the database technology, right? So Instant JChem is already a GUI. It's an end user application. If you want to integrate Chemexon's chemical intelligence with other applications, then you would have to use JChem, the JChem engine, which is available as a microservice, as an API, as a backend database. It is available. So you can have the functionality that I've shown you here in a different interface, but the background can be with Chemexon's JChem engine.
All right. Thank you so much, Mr. Surojit, for that highly valuable and detailed presentation. And thank you all the excellent questions.
So thank you all for attending. It was a pleasure hosting this workshop. I hope to see you soon again in the next ones also.
Yes, and while we try to address as many as queries as possible, some may remain unanswered due to less time. So please don't worry. Our team will review all the questions and provide detailed responses by email after the session. With that, we officially conclude today's webinar. On behalf of Advent Informatics, I extend a heartfelt gratitude to Mr. Surojit Sadhu for sharing his expertise and guiding us through the powerful feature of Instant JChem and Plexus Connect. A big thank you to all wonderful audience as well for your time, your curiosity and engagement. So we look forwarding to see you again in our upcoming webinar. Have a great day ahead and goodbye.